see you've come back for more AP Chem. We are going to be wrapping up calorimetry and its applications today when we talk about the calorimetry of chemical reactions and processes. And there are a couple different angles that I want to show you guys because there are a ton of different ways that you can kind of see this on the exam. And I was just reviewing a lot of past FRQs, and man, they really love to put enthalpy questions on there and calorimetry questions. And I think that's twofold. One, it shows that you can kind of do the math and kind of wrap your head around a lot of those things because there's honestly a lot to do. And two, it lets them know if you have any experience with the lab or even talking about how the equipment works. So I think that's why it's so popular, and you see it in a lot of exams. And I'm going to show you a couple ways that you can kind of potentially run into shortcuts on the exam, and hopefully that helps things a little bit too. So we're going to start off right away with a problem because at this point, you know how to do, you know how the calorimeter is set up, you know kind of hopefully mentally how that's all set and ready to go. So we're just going to dive right into a problem. So if at any point you want to pause and like copy this problem down and, you know, then give it a try for yourself, you're more than welcome to. I'm going to read through it and work with this first example, and then we'll go from there. So and this is something that you actually probably have heard of before. Gram for gram, fats in food have much more chemical energy than sugar. One component of fat is a chemical called stearic acid, which is C18H36O2. When a sample of 1.02 grams of stearic acid is burned completely in a bomb calorimeter filled with 1,250 milliliters of water, the temperature of the calorimeter rose by 7.2 degrees Celsius. Calculate the molar heat of combustion of stearic acid in kilojoules per mole. Now, like I said, you're probably going to see this problem broken up into two parts. You're going to have it calculate the moles somewhere else in the problem would be my guess, and then it'll give you the heat and ask you to find the molar heat of that reaction. So if you want to give this problem a try right away, you are welcome to kind of go ahead and do that. I'm going to switch over to my doc cam so you can see me working through it, and then we will get started. Get this focused for us. There we go. Okay, so we've got our problem here. And when we start looking over these problems, a lot of times there's a lot of information involved here. So the most important part is going to be to start off figuring out what we're going to solve for in the end. So as we read through this, we know we've got this stearic acid here, which has this huge formula. We're putting it in a bomb calorimeter, got 1,250 milliliters of water. So if we want to draw a picture of this, got our bomb calorimeter. Remember, the bomb is kind of that little container inside. And so we ended up putting up 1.02 grams of that stearic acid inside of there. And then inside my calorimeter, I've got 1,250 milliliters of water, which if we assume the density is 1 gram per milliliter, it's 1,250 grams of water inside. And it's telling me that my temperature goes up 7.2 degrees Celsius, and I want to figure out kilojoules per mole for my heat of combustion. Now, the kilojoules per mole is kind of a weird thing. It's like, what moles of what? What are we talking about? And in this situation, it's kind of always moles of the overall reaction that happened. And so it's really important when we talk about this to designate a chemical that's in the, I guess, circle of consideration for this particular problem. Sometimes it'll be very obvious, like in this one, it's just stearic acid because we haven't really talked about much else, and it's combustion of the stearic acid. There's an implication in this that we have unlimited oxygen, so that's a thing as well. But in other situations, you may be asked to determine the limiting reactant, and then that enthalpy change is going to be relative to the moles of how much that limiting reactant had. So in this case, it's not so much of a big deal, but I'll show you guys kind of what we're talking about when we get into limiting reactant things. So we need to get it into kilojoules per mole. Like I said, probably the first thing they would do is early on, they would ask you what the moles or how many moles of this reacted in the first place. So it tells me that I have 1.02 grams of this stearic acid, which is C18H36O2. Beefy. It's a big one. When you calculate the molar mass for that whole thing, it is over 200 grams. So if we set up our conversion to moles, it's 1 mole of C18H36O2 is equal to a whopping 284.468 grams. So it's large and in charge there. And what we're going to do is we're going to first figure out how many moles of this stearic acid reacted. And when we do that, there's not really any stoichiometry that needs to happen because we already have the grams here and we're just converting to moles. So when we do that math, I ended up getting 0.00359 moles of my stuff reacting. Now, if this were a limiting reactant problem, we would have to sort out which one is the limiting reactant and then use that limiting reactant for our problem. In this situation, I should back up. In limiting reactant problems, I'm normally all like team, hey, let's figure out how much stuff we're actually making. But in this case, if we would have to figure out a limiting reactant, it might not make sense for us to go all the way to a product. We might be able to look at moles and compare later. And like I said, I'll show you that in a minute. So I've got my moles here. Now I need to figure out the kilojoules that went into this calorimeter. So at this point, you should be professionals at this. We know that our water's change is going to be figured out through the Q equals MC delta T equation. So the M is going to be, now this is a little weird here because it's happening in a bomb calorimeter. There isn't a mass of the solution that you necessarily have to figure out. We're just going to worry about the water. If these are mixed together and you're creating a overall solution for your reaction, then you need to take it into consideration. But since it's in the bomb, you don't have to worry about that. So it's going to be 1,250 grams of water times 4.18 joules per gram degrees Celsius, our favorite specific heat. And then our temperature change is going to be 7.2 degrees Celsius. So we want to plug in our answer into a calculator and then get out an answer, plug in our numbers into a calculator, get out an answer, and you should get 37,620 joules. Okay. Hopefully this is making sense because you've seen the heat of solution stuff. Now remember that this is the sign for the Q for the water because the water gained that energy. When I want to figure out my enthalpy of my reaction here, okay, so my delta H, if I want to get that into kilojoules per mole, I've got to remember that I need to change the sign, but the value is still the same. This guy's got to get into kilojoules because the units need to work out. So it's 37.62 kilojoules. Just divide by 1,000 there. But when I put it into my enthalpy calculation, oops, see, screwing it up. You got to put the negative sign there. So it's negative 37.62 kilojoules. And I'm going to divide that by our number of moles. So 0.00359 moles. Now, 1 gram is not a lot of stuff. So when you think about like how much energy is coming out of there, it's going to be a big number because this is a tiny number in our denominator. And I ended up getting a negative 10,479 kilojoules per mole, which is a lot of energy. But if you think about it, a gram of fat, they typically say is like 9 food calories per gram. So that's 9, it's a lot of joules to start off with. So it's 9 kilocalories, which means it's like 36,000 joules. So we're talking a lot in there. So our enthalpy for a reaction is very high. Okay, so this is kind of just like we had before. Once you know the moles of the reactant that you're focusing on, you can just figure out your joules and divide by the moles. Okay, now I told you about the limiting reactant stuff. So let us chat about that for a second. I looked back at a couple past AP exams because I think that it is important for us to know some things. A lot of times in calorimetry experiments, they're going to talk about a limiting reactant problem because they really love to integrate different topics onto the AP exam. So they'll throw in, intermolecular force question in here as well. So here's one that we took a look at. This is, I believe, the 2013 exam. So at the very beginning there, it gives you this reaction, right? And it gives you this data table. And then it gives you 4 trials of a enthalpy change reaction. So this is what it's saying. And we're implying that it's a calorimetry experiment. So we've got 100 milliliters of 1 molar HCl, differing masses here of this MgO. And then we have some different temperature changes happening here. Okay, so then it says, which is the limiting reactant in all 4 trials, HCl or MgO? Now, if you wanted to, you could, and I seen this on the exam. I handed this out as a question one year. Everybody quick went and they ended up doing the math. So they figured out the moles of the HCl, the moles of the MgO, and then did a comparison. But if you have to do that for 4 trials or even 2 trials, it is a lot of work and it takes a lot of time. You don't have that much time on the exam. So what you want to kind of do here is take a look at the data that they're giving you, because if you remember the ACT, there's always kind of some suspiciously coincidental data here, and that's the case. So if you look at this situation here, I have 100 milliliters in every trial. So that is a control. And then I have 2 different masses here, okay? Now, if you think about this, if the HCl is my limiting reactant, when I change the amount of this, the temperature change should not change at all. And if you look at this, I've got 0.25 grams and my temperature goes up a degree. In this case, 0.5 grams makes my temperature go up more than 4. In this one, 0.25 makes my temperature go up 2 degrees, and then 0.5 makes my temperature go up about 4 degrees. So we have different magnitudes of temperature change when we change the MgO. So your justification can actually just be that the MgO is my limiting reactant, because as I change the amount of magnesium, I get a different temperature change for each of the reactions. And doing a delta T calculation, I didn't even have that done. I just did some quick mental math, is a heck of a lot faster than doing a molarity calculation. And from history's perspective, we don't like molarity calculations. So just keep that in mind. Another example. Okay, take a look at this one. You got your balanced equation here. It says, in the experiment, the student uses solutions shown below, and you have, again, suspiciously coincidental data. So if we look at this, we have 0.5 molar solutions of every reactant in there, and we have the same volume. Okay, and then question C on this says, using the balanced equation for the oxidation reduction reaction, which is just the reaction above there, and the information in the table, determine what's the limiting reactant. Okay, so now you look at this and you go, I have to do 3 calculations? You're crazy. And the answer is no, don't do that. They are suspiciously coincidental pieces of information. And if you think about it, if I have the same volume and molarity, it means that I have the same number of moles. We've talked about this ad nauseum. If you take your volume in liters times your concentration, that gives you your moles. So if I have the same volume and the same molarity, that means I have the same number of moles of each of these, right? Right? Okay. Now look at our balanced equation. It is a 1:4 to 2 mole ratio. So that means if I use up 1 mole of this Na2S2O3, I am going to use 4 moles of the NaOCl up at the same time. And so if you think about what's going to run out first, it's going to be this NaOCl, the sodium hypochlorite here, because this one's going to run out faster if we have the same number of moles, because I use it up 4 times as fast. So again, the expansive limiting reactant math isn't necessary if they're giving you this big data table. So just something to watch out for when you are doing these problems, because there is a time crunch, especially on the FRQs. I mean, all of it's a time crunch, honestly. So just be careful with that. Okay, so last example is kind of a riff on a problem. It's a calorimetry problem, but not in the same way we've been looking at it. So a thermite reaction, the reaction between aluminum and iron 3 oxide produces a tremendous amount of heat. They actually use it for welding, like railroad ties together. So it produces molten iron as a product, and it ends up like binding the 2 railroad ties together. So it's kind of cool. Anyways, if you look here, it produces 852 kilojoules when 2 moles of aluminum react. So that's like 60 grams. It's not a lot. You get a lot of heat out of it. Very exothermic because heat is a product here. So question A says, if you begin with 10 grams of aluminum and excess Fe2O3, how many kilojoules of heat are evolved? Okay. Second part, if you heated a 2-liter container of water at 22 degrees Celsius with the heat generated by the reaction, what would the final temperature of the water be? So we've got a almost like a stoichiometry problem up here at the top. But then we have a MC delta T problem, but we're looking for a T in this case. So I just thought it was a kind of a different wrinkle and wanted to show you. So if you want to pause the video and give this a try, go ahead, and then we will work through this. All right. So example number 2, you begin with 10 grams of aluminum and excess iron 3 oxide. How many kilojoules of heat are involved? So in an AP exam, this is what the problem is going to start off as. It'll be its own A question. All right. So this is a stoichiometry problem because I know I've got 10 grams of aluminum and I want to figure out kilojoules. So I've got a balanced equation. I know I'm going to do stoichiometry kind of right off the bat with this. So I'm going to start off with my 10 grams of aluminum. And you know, starting information needs to go into moles. So 1 mole of aluminum is equal to 26.98 grams, right? Grams will cancel out. We're in moles. And then because I am doing a stoichiometry problem, I need to pay attention to the coefficients here when I come to my mole ratio. So it's going to be 2 moles of aluminum. And then the 2 moles of aluminum are for 852 kilojoules. If I would multiply all these coefficients by 2, that enthalpy value is going to get multiplied by 2 as well. So it's dependent on the coefficients. Okay. So this is going to get me my energy that I need. And if I put that into my calculator, I'm going to make 157.89 kilojoules. Okay, so 10 divided by 26.98 times 852 divided by 2 gives me 157.89 kilojoules. Okay, so that'd be part A, and hopefully that seemed relatively easy to you. For part B then, kind of the next one down the line, they're going to ask you to use your answer from A, that 157, and heat a 2-liter container with it. So you got this container. We're going to add a Q value to this, right? Q equals MC delta T. But the thing is, our specific heat, like if you think about setting this up, our mass is going to be the mass of water, which if it's 2 liters is 2,000 grams. So nothing surprising there. But our specific heat is 4.18 joules per gram degree Celsius, right? So when we put our heat in from this reaction, that needs to be in joules as well, or we need to make sure that the specific heat is converted. And I think it's easier to just turn this into a joule value. So I'm going to have 157,890 joules equal to my Q equals MC delta T. And I'm trying to find my final temperature. You could attack this in one of 2 ways. You could put your initial temperature in here and do the distribution if you want to. I think it's a little bit easier to just put in delta T and then deal with the delta T later. Excuse me. So normally I am all team do your variables first, but I put them in as we were talking, so I'm just going to commit to it. So I'm going to divide by 2,000 grams times 4.18 joules per gram degree Celsius on both sides. Okay. If you think about units, joules and joules are gone, grams and grams are gone, and that's fantastic. So we are left in a situation now where my delta T, when I put it in, is going to be 157,890 divided by these 2 numbers in my denominator. Put parentheses around them in your calculator. Okay. So my delta T comes out to 18.89 degrees Celsius. And I'm heating it up because I'm adding that energy into there. So my delta T is going to be 18.89. If you think about delta T is equal to T final minus T initial. So if I want to find T final is equal to delta T plus T initial, right? So in this case, my T final is going to be 18.89 degrees Celsius plus 22 degrees Celsius, and that gets me a temperature of 40.89. I have seen all of these types of questions on the AP exam, hence the reason I'm running through them. So it's a lot to digest, and there's a reason why we've kind of spent a lot of time on this. It's because you can see it in so many ways, and you see it on every exam one way or the other. On a multiple choice or an FRQ, you are going to get an MC delta T question somehow, some way, I don't even know. So if you have any questions, make sure you get them cleared up. We are not even really scratching the surface at this point with enthalpy. We have so many more ways that we have to figure it out yet. I think we've got 2 or 3 more ways. So we are just not even to it yet. So if you find yourself struggling, please make sure you get things cleared up. Otherwise, take a crack at your homework and good luck.